Welcome to Lecture 9 in DIY transcriptomics. It's been a really long journey to get here, and I think that there are probably many of you in the course who expected that today's topic might be a topic presented much earlier in the course. And I think that's true in a lot of cases with RNA-seq data analysis. Is everyone immediately goes to differential gene expression. We did the experiment in the first place because we really wanted to know which genes were differentially expressed between our disease and our healthy, between our knockout and our wild type. And so it's natural to think of RNA-seq analysis as really being rooted in differential gene expression. To some extent that's true, but I hope one thing you've taken away from what we've done in the course thus far is there's a lot of useful and important things that need to be done before we actually get to the point of testing for genes that are differentially expressed. So that'll be our topic for today. And just to kind of ground everybody here, we're really rounding the corner on this course. If we scroll down to today's lecture on differential gene expression, we will spend next week taking the differentially expressed genes and finding coordinately expressed transcriptional modules that we can then feed into downstream functional enrichment tools like gene ontology enrichment. We'll also talk about gene set enrichment analysis, GSEA. Again, I think these three lectures, differential gene expression, modules, and functional enrichment, are what most people think of when they think of RNA-seq data analysis. So that'll take us through next week. You'll be at your next Hackdash then, which will obviously incorporate a lot more of the content from these last three lectures. And then we wrap up the course by talking about how you document and do all of the things we've done in the course, but in a really reproducible way. Okay, so we're going to talk about differential gene expression. And really that involves a few key learning objectives. And, fortunately or unfortunately, depending on the kinds of topics you like, a lot of today is rooted in statistics. Unfortunately, I am probably neither the person to teach you that, and this is probably not the course to do that in. We just don't have time to deal in and really open up the hood and poke around on what's happening when we run some of these functions. But in today's lecture, on the lecture page, I provided videos, again, from the StatQuest series on several of the key statistical topics that we'll touch on, and I'll mention those when we get to them. So the first thing we need to do is talk about how to set up our what we'll call our model matrix or design matrix that will really articulate how a linear model will be used to analyze our data for differential expression. We'll then talk about how to set up in R the pairwise comparisons that we want to actually test for gene expression between, and we'll do that using the contrast matrix function. We'll then use the Lima package to identify differentially expressed genes, and the Lima package is this really venerable package linear models for microarray analysis. That's where the word Lima comes from. It's been around, as the name implies, since the days of microarrays, and it provides a lot of functions and tools for analyzing gene expression data. We'll then take the results from that differential gene expression analysis and we'll feed it right into things you're already familiar with, how to make static plots, how to make interactive plots. You'll learn how to make volcano plots today. And then new in this iteration of the course, we're going to actually talk about how we can identify differential transcript usage. After all, we carried out an alignment or mapping of our reads to the transcriptome, and it would be nice to actually leverage that transcript level information in some way. And thus far in the course, we really haven't. We summarized our transcript level data to gene level data and didn't really explore transcripts and alternative splicing and differential transcript usage. So we will just touch on that today. It's an optional part of the code, and this is the step 5 script that you'll download. But I'll demonstrate it for you. There's some things you're going to need to do in order to actually reproduce what I'm doing. Okay, so just to kind of emphasize, we've been working up to this point the entire course. This is as much as I can possibly make it. This is a somewhat linear course. We keep progressing towards the end goal of having a detailed analysis of our RNA-seq data. And so that by and large happened by taking our data and getting it into R and understanding what those units of FPKM, RPKM, TPM really mean, why we use log2 scales, how we control for comparisons within samples, and how we normalize, filter and normalize to control for comparisons or prepare us to make comparisons between samples. And really importantly, the normalization method that we used from EdgeR, this calc norm factors, is really to help us now be able to make these between sample, between condition comparisons. One thing we really won't touch on, but I just want to make you aware there's still active development in the way we think about how to understand signal and noise in RNA-seq experiments. And some of those are right at your fingertips, but we haven't really used them. So one is, and we talked about this back in lecture 3 when we were talking about Callisto for read mapping, is that Callisto and other pseudo-alignment tools like it can, by virtue of being able to do read mapping so quickly, they can do bootstrapping of that read mapping step, essentially doing many of those read mappings with subsets of the data, and in doing so, each time generating quantifications of each transcript in each sample, and any variation between in a gene's expression in a particular sample between all these different bootstraps is really technical variance. It's not real, right? There's nothing biologic changing when Callisto reaches in and grabs a subsample of reads and redoes the quantification. So by taking these repeated bootstrappings of quantification data, you can actually start to understand uncertainty in your counts for RNA-seq data, and that uncertainty can be used to improve our ability to call differentially expressed genes. We did not use the bootstraps functionality, in part because it's undergoing some changes right now, and also because it makes the files larger, and I think there's still development in how these bootstraps would be used downstream. So we sort of skipped this, but just so you know, this is an area that's developing, and the way in which this uncertainty will be valuable is exactly in the steps we're doing today, in things like understanding technical variance, taking that into account, and improving our ability to know what's truly different. So there's some terminology we need to cover for today. I think everybody is probably thinking about DGE, and I certainly have referred to it as DGE analysis thus far in the course, and that's the idea of differential gene expression. That really refers to a change in the expression of the total output from a gene, right? And so in this case, we'd be talking about gene A across 3 conditions, and let's assume we have some statistics here available to us, and we can think, okay, this gene is increased, is differentially expressed. It goes up in condition 2 compared to condition 1, and it goes down in condition 3 compared to condition 1 and condition 2. All right, so that's differential gene expression. That is the topic of today's lecture, but we're also going to touch on these 2 other concepts as well. And one of those is differential transcript expression. And in that case, we're not talking about a gene, we're talking about a transcript and how it differs between conditions. And so you may be wondering, why didn't we just do differential transcript expression this whole time? I mean, we had our data at the transcript level. And the answer to that is sort of twofold. The first is, I think inherently a lot of people relate to gene level data in a more simplistic or straightforward way. We can relate to gene symbols perhaps easier than we can relate to these large ensemble transcript identifiers. So part of it is just convenience, but there's also recently been evidence that transcript level data is not as reliable as gene level data. So let me explain that a bit. So, and I encourage you to check this out. It's linked on the reading for today's lecture. And that's that genes can really be more accurately measured than transcripts. If you take transcript level data versus gene level data and you look at actual transcripts per million versus what you would have estimated the transcripts per million to be, you get a much better correlation when you're measuring your data at the gene level than the transcript level. We have a lot of transcripts here where the actual TPM is higher than the estimated TPM. And you can imagine how there are many scenarios where, if we take this hypothetical one, for example, where you may have reads aligning or mapping to a region of a gene. And if we were to use this data to estimate the expression of the gene, so ignoring its isoforms and just considering there are 1, 2, 3, 4, 5 possible exons in this gene, we would, we would have a reasonably accurate idea of the expression of that gene. However, if we decided we wanted transcript level quantification of isoform A and isoform B, then we would have a much harder time making an accurate call of that expression from data like this, because those reads map to exons that are shared between isoform A and isoform B. And whether you were to try to make a call for assigning those reads to isoform A or isoform B, you might be ultimately wrong. So we don't get stuck in this sticky situation if we keep things sort of at the gene level. And I'm being very sort of simple about this. Again, I encourage you to read the Sonesson paper for a detailed description of this process. And it really has, it's at the heart of how we read our transcript level data into R and use that data to generate counts that help us control for this. And so they've gone on to show in the same study that if you aggregate your transcript data to the gene level, you actually get better estimations of gene expression, more accurate estimations of gene expression. This is a false discovery rate compared to a true positive rate. And you can see that if you, the upper lines here are aggregating transcript level data to gene level data, you get a much higher true positive rate at, while really not compromising your false discovery rate. But there's another aspect of this, and that's differential transcript usage. In differential transcript usage, we really have to change our thinking a bit. And instead of thinking about whether a transcript is expressed higher in one condition versus the other, we are taking the total output from the gene, and we're asking what proportion or fraction of that gene's output can be accounted for by isoform A1 versus isoform A2 from this gene A. And so if we think of this as 100% of the gene's output, and if we imagine this gene's expression is not changing across these three conditions, then we could potentially say, all right, in this first condition, isoform A is weakly expressed, and most of the gene's expression is coming from isoform A sub 2. But when you change those conditions, when you go to condition 2 or 3, there is this isoform switch, if you will, where now most of the expression from gene A is coming out as a result of expression of this isoform A1. And so that as I referred to, is frequently called isoform switching, when the relative or proportion or fraction of a gene's expression is accounted for by different isoforms across different conditions. And these concepts are not mutually exclusive, so you're not dealing with one or the other. And I'll give you examples at the end of the lecture where you can have a gene that is differentially expressed that has different transcript expression between conditions and different transcript usage. Okay? And again, we'll root these in some real examples as we get further along in the lecture. So the take-home messages are, you now understand that these are different: differential gene expression, differential transcript expression, and differential transcript usage. And you understand that we actually, even though we didn't really delve into it in great detail, we were doing something good at the beginning of the course by taking our transcript level data, our transcript level counts, and summarizing them to gene level, because it gives us a more accurate estimation of the output from those genes. All right, so then how do you think about the appropriate method for carrying out DGE, DTE, DTU? And this table also from Sonesson sort of summarizes, at least at the, in 2016, and I think this is still largely true, the sort of state of the art for approaching these analyses. And I want to point out that in all three cases, Callisto and the other pseudo alignment tool, Salmon, are all appropriate read mappers for all three of these approaches. And what's being proposed in Sonneson is that the TX import package, which we use to read our Callisto data into R, is the appropriate way to then move that pseudo alignment data into the R environment. All right, and then today we'll be touching on VUM and Lima, the sort of combo function from Lima and the Lima package in general, for then carrying out differential gene expression analysis. We will then, at the end of the lecture, touch on how to use DexSeq and a whole lot of other tools wrapped up inside one R package to carry out differential transcript usage. We aren't really looking in this course at differential transcript expression, and for a lot of reasons, I tend to feel it's better to aggregate these to the gene level. And there's evidence, of course, in this paper to support that. And again, I like to have that connection to gene symbols. Okay, so we'll touch on DexSeq just as a tool today. We won't really talk about how it works. So that's really where I want to sort of start things. And at this point, we'll head over to our studio and we'll begin talking about today's plan. Okay, we'll pick that up in the next video.